Hello, everyone. Glad to be back in Columbus. We're going to start a new unit today on linear classification. And let's first start by introducing the demo of the application. So in this case, it's about diagnosing breast cancer. And so what's typically done is a tissue sample is extracted and stained, and then someone looks at those different images in a microscope, and they try to diagnose in one of two categories, either malignant or benign. And here you get the sense of classification. The task, different from regression, where we were trying to predict a real number, now we're trying to predict a category. So that's the big difference from before. And so another thing that this medical person does is, so basically they collect all these measurements, and then they also make a diagnosis. And so we want to know if we just had the measurements from the different things they scored here, could we do a better job of making the diagnosis just with machine learning? So we're going to be using this Wisconsin breast cancer data set, and there are 683 samples, 9 different features. These are the features here. And one thing you'll notice is that these features are all discrete, so they're all integers between 1 and 10. And so that they're still ordinal, but we're going to have to change how we plot them. We can't plot a scatter plot, as we'll see in a moment. And again, the target is categorical, malignant, or benign. And first, this data set, it happens to be the number 2 represents benign, and the number 4 represents malignant. But there's nothing really special about those two numbers. The key is that there's 2 categories. You can use any 2 numbers to, mark the categories. The values are not important, just the fact that there's 2 different ones. Okay, so let's try to visualize the data. So usually what we do is we make a scatter plot, right? But here the trouble is that all our features are integers. And so here actually we're just going to plot, versus 2 of the features. So that would, if we looked at those 2 features together, they would always fall on this grid. And that's not very useful because a lot of points would fall exactly on top of each other, and you wouldn't be able to see when there's many points stacked on top of each other or not. So what we do instead is in the code on the right, we make the dot bigger if there's more points that fall into that particular, bin. So you can see that like this bin down here, and we're using 2 different colors. So all the benign samples are marked in green, the malignant ones in red. And so like down here, for this combination of features, you can see that almost all of the samples are benign, though there are a few malignant ones in there too. So that's just an example of this data set. Any questions so far? Okay. So let's take another look at this. So how would you classify a test feature? So I give you, like a particular point somewhere on this curve. How do you classify whether it's benign or malignant? So just sort of like imagine yourselves not as an expert. We haven't learned about how to do this, so just imagine if you had to create a method, what would you do? Any ideas? Nobody has any ideas? Yes.
Because there's some bound, if it's like based on the part of the band is assigned to one of those
Okay, we could make a boundary. For example, maybe we could make a boundary like this. And then if it's on this side of the boundary, we'd say benign. But if it's on this side of the boundary, it's malignant, right? And so like depending on where a given feature pair lines up, that would be malignant, this would be benign. Okay, yeah, that's exactly what we're going to do. We're going to get into a lot of details about how to do that, but that's what we're going to do. So let's step back and talk more generally about binary classification. This is sort of the task that we're performing now. So we're given training data, similar to what we saw in regression, where we have the I is the training sample, we have feature vectors xi and targets yi. But the difference now, like I said before, is that the targets are categorical. So we're going to assume, just because some of the math works out conveniently, that our targets are going to be the numbers 1 and -1. But there's nothing really very special about that, except that some of the math simplifies a little bit. Another common thing you'll see is if the targets are 0 and 1, or there's even other options, like with this data set was 2 and 4. Okay, so the point is that there's just 2 classes for y. And so we saw one example, are these cells cancerous or not? Another example could be like this. You get an image, you take all the pixels in that image, and you rasterize them to a vector, and then you want to know, like, is this a weed or a crop? And you code weed or crop with those 2 numbers. Okay, so many, many examples of this you can imagine. So one way to think about this is that we want to design a classifier. A classifier in this case would be a function that takes in a feature vector x and produces an estimate of the label y hat that is either going to be 1 or -1. No other answers are allowed, right? It needs to be 1 or -1. Now, if the true target is also 1 or -1, either it's going to agree with y hat perfectly, or it's not going to agree. So really, it's not about how close y and y hat are, something like y minus y hat. It's not about that anymore. It's about whether they agree or disagree. And we would like that they agree with high probability or often. That's our goal. Okay, now, something we can do now that is a little different than what we did with regression, as we just discussed, is that we can define that function by decision regions. So, in particular, if you think about all the x for which fx is -1, that would be one region. We could call that the region of -1. And then you could say, what are all the x such as fx equals 1? So here's an example where there's 2 features. So we would have like x1, x2. And according to this classifier, whenever it's over in this region, fx is -1. And whenever it's in this region, fx is +1, just as an example. Okay, so that's our goal. Any questions? Okay. So now, binary classification in general allows you to define these boundaries that are nonlinear. But we're going to simplify things a bit, at first at least, and we're going to consider binary linear classification. And in that case, the boundaries are going to turn out to be lines in 2 dimensions, or planes in 3 dimensions, or more generally hyperplanes. And this is a 2-step procedure that we're going to do. So the first step should look very familiar from linear regression. You're going to make something called a score, or compute a score, which is, we're going to call it z. And z is going to be some bias coefficient b, or intercept coefficient. And then we're going to sum over all the features, j equals 1 through d, of xj times wj. Okay, now if you look closely, this looks a lot like linear regression, right? In linear regression, this was like our beta naught, and these things were like our beta j. So I'm just changing notation a little bit to be consistent with what you'll find in other sources. We could have written everything as we did before. We could have called that beta naught and these beta j. It's mathematically the same thing. It's just that I'm switching the notation up to be consistent, like I said, with other sources. And then you can see that the output of this is some form of real number prediction. But this is not the final prediction for us because remember our final prediction needs to be 1 or minus 1. So that means that there's one more step is we do a thresholding. And in this case, we're going to set y hat equal to 1 if z is greater or equal to 0, or minus 1 if z is less than or equal to 0. Okay, so those are the two steps in the process of linear classification. Assuming you have already designed these coefficients b and the different w's, you use your test features to give you your test score, and then you threshold that score at 0. If it's above 0, you report 1. If it's below 0, you report minus 1. And now your target predictions are guaranteed to be 1 or minus 1. And the weights and intercepts, or sometimes called the bias, are learned from the training data set. So what we'll get into is later today is how we do that, but there's some way of doing that. Any questions so far? Okay, so so let's think about what happens at the decision boundary. So remember that based on this way of thresholding things, you can see the boundary is right when z equals 0. And so z equals 0 is a special set of points x that lie on that boundary. So this is the decision boundary or the hyperplane. It's the set of feature vectors x such that this b plus x transpose w equals 0. So in this plot, it's all those points x here. This could be like x1, x2. Okay. So that's the boundary that separates the decision regions. And so that's like the place where you're most uncertain about what the label is. When you're right on that boundary, you really don't know whether it's 1 or minus 1. In this case, we happen to assign it to 1, but it doesn't really matter that much in practice which one you assign it to, because the probability that a point falls exactly on that line is pretty much going to be 0. Okay, so when you look at these pictures, you can see that the boundary is in fact a line in 2 dimensions, or if you had 3 dimensions of data, another one coming out, it would be a plane, or if you had 4 features, it would be a 3-dimensional plane, which we as humans can't really visualize too well. So in general, we call it a hyperplane. Hyperplane is sort of like a plane in generic number of dimensions. Okay, so that's linear classification. So it's called linear for several reasons. Importantly, if you think about z is a linear function of the weights. And that is going to be critical for us in order to do the design, similar to how in least squares, that linear property was also critical for us to derive things in closed form. But it is also linear in x. And that linearity in x is what gives us this hyperplane behavior. So there's sort of 2 forms of linear in this classifier. Okay, any questions? Everybody good? All right. So one thing that can happen that we very much like when it happens is when the training data is perfectly separated by some sort of linear boundary. So here I'm saying like the squares might be samples with y is 1, and maybe the circles are samples with y is minus 1. And here you can see it was possible to find a linear boundary where it's perfectly classifying your data. Okay, so that's what linearly separable means. It's really a property of the data set, the training data. so that's what we mean. And as you can see, if you can find one linearly separating hyperplane, you can probably find a whole bunch of them. Okay. So in this case, this is great because that means that if the test data is like your training data, you can expect to do really well. Right? You should be able to classify perfectly or near perfectly. Okay, but that doesn't always happen. In fact, in practice, it usually doesn't happen. There's many different ways that this problem can manifest. So, like if you have data like this, where the red points are one label, the blue points are another label, there's no way that I can come up with a linear hyperplane that separates that cleanly into blue and red. Here's another picture where there's this red point over here, and once again, there's no way I can come up with a line anywhere that separates this perfectly into blue or red. Now, of course, if I could make a nonlinear boundary, it is possible to do that, but here we're considering only lines, so this is not linearly separable. And then here's another example of non-linearly separable. Okay, so you can see that linear classification imposes some restrictions. It's not the most powerful thing that we could do, but still, there's a number of reasons we're going to consider it. First of all, it's relatively easy to understand compared to methods with nonlinear boundaries. Number two, it facilitates feature selection, meaning we can figure out which features are most useful in predicting the target. Maybe if we're doing this breast cancer detection, we might want to know which of those different, the data they collected from the tissue slides, which one was most important. You can also, as we know with feature selection, you can navigate the bias variance trade-off by removing features that don't really help that much. So that's something you can do quite easily with linear methods. Also, we saw in regression that it's possible to perform nonlinear operations on your features and then still be able to do the design linearly with the coefficients. So we saw that with, let's say, polynomial regression. You can do that here as well. And there's other things you could do. For example, if you have this situation here, you can see that the boundary we want, which is the circle, is not linear in x1 and x2, but let's say we constructed this new feature. Number one, let's suppose that this is the origin here, and let's say we compose this new feature, which is basically the radius from the origin. So with that single feature, if I just thresholded that feature, then I can basically make this boundary here, and I can perfectly separate my data. So the point is that if you can do something clever with some sort of nonlinear transformation of your features first, then you can apply linear classification and get really interesting results. And in fact, that's exactly what happens with the most sophisticated neural networks and so on. At the end of the day, their final stage is linear. And what they do up till that stage is they do all sorts of sophisticated feature processing, nonlinear stuff to get the results so that that final linear stage performs really well. Okay. So there's many reasons for looking at linear classification. Okay. Any questions? Okay, great. All right, so we know something about designing coefficients, and so back here we saw that there's a lot of similarities between the problem that we have and with linear regression, and so we might say, well, can I just maybe do something like least squares linear regression to solve this problem? So let's see how that would go. So now we're getting to the problem of how exactly do we fit the coefficients. So one idea would be, let's minimize RSS. We could do this by the squared norm of y minus the, I think I want to use the A matrix here, yeah. The A matrix times a vector, or I have the B on the top, and then below it, the W vector. So if you remember, this would be like a vector of scores Z. And so here we're just designing the scores to directly try to predict the true plus minus 1 labels in Y. Of course, once we can fit our coefficients using least squares like that. Once we have those B and W, our Z's are not going to be plus or minus 1. They're not going to be binary. However, we could still do the thresholding once we're done. And this is basically how you'd, for a test feature vector X, you could transpose it to build this row vector, inner product between that and your least squares version of this vector will give you your score Z, and that score Z could be thresholded and compared to Y hat. Okay, so it sounds like pretty straightforward. Let's see how well this works. And we're going to look at just a toy data set that has a single feature. And so this feature I'm plotting along the horizontal axis. And then I'm plotting Y, which are the labels on the vertical axis. So here's the data set. These are the points I collected. So you can see that I have 4 instances of Y being minus 1 with those corresponding feature values X. And then I had 4 instances of plus 1 at these feature values X here. And so if I train least squares, so you can just sort of forget this green line now. Just imagine you're doing least squares with this data set. You're looking to build a line. This is going to have an intercept here of B and a slope of W. And you can see that the line is trying to minimize the sum squared of those errors, right? Those are the errors between the true and predicted labels. So if you do that, actually things work out quite well. You get this line here. This is the function Z as a function of X. So it's your score. It's what the linear part of this classifier is predicting. And then once you have that Z, then you do this thresholding to get Y hat. And so if Z is greater than 0, which happens in all these cases, you use threshold up to 1. This is what you finally report as Y. And if Z is less than 0, which happens here, you threshold down to minus 1. Okay, so that's where you get the final nonlinearity of your classifier. And everything works out perfectly. You can see that the prediction we're making for Y is perfectly matching our training data. Okay, so it seems like everything is going well. Let's just make one small change to the data set. For this last point here, we're going to move that point out here. It seems like that shouldn't really affect things too much because, in some sense, like as you get away from this, like when you're right in the middle, this is where it's kind of difficult to figure out how you should be classifying the data. But as you get farther in these directions, it seems kind of obvious, which prediction you should make, right? So in some sense, these are the easiest points to classify. And by moving this out to here, in some sense, we're even making it easier. But this messes up least squares because least squares is now trying to minimize the sum squared difference like that. And this is what it does. It comes up with this line. So that's our Z. But then we threshold that Z. So wherever Z is positive, we report 1. Whatever it's negative, we report minus 1. And you can see that we are incorrectly classifying this test sample. So if X was this, we would be predicting this, whereas the training was this. So it's not even matching the training data, which you can see is a pretty big reason for concern. So something about least squares RSS is not really working out here. So we can say RSS is not the right loss function for classification. So we're going to try to come up with something better today. But if nothing else, these plots here give you, more insight into how the classifier works. Are there any questions about anything in how these plots are constructed? Are they making sense? Everybody good? Okay. Okay, so we can take the same least squares approach and apply it to the breast cancer data set. And we have sort of the same issue. So I don't know if there's really any official name for this, but I'm calling this kind of data set symmetric because there's a lot of symmetry in those points. And then this one I'm calling asymmetric because this is spread out more than this. So if you look at the breast cancer data set, at least with these two features here, you can see there's something similar going on. So the benign labels are kind of squeezed in this region, whereas the malignant labels are like spread out here. So it's very similar to what was happening in the 1D case, except it's now in 2D. And the same thing happens. When you fit with least squares the classifier boundary, you get that blue line, which you can see is it's missing, it's not giving you the correct prediction for all those malignant labels here, which we said sort of intuitively before, just as a human, it seems like you want to put your line over here, right? Your boundary. But somehow least squares is putting it over here because it's trying to minimize the squared error of all those points there and these points here. So it's sort of moving this out to be more centered between those two data sets. And that's not what we want to do for classification. So, okay, so let's see. So for the decision boundary, sorry. Oh, that's right. So what we can do for the decision boundary is we can, for this problem, we can actually write an equation for this line as minus b over W2 minus W1 over W2 times X1. And the way you can get that is you just start over here, and you rewrite this as b plus X1 W1 plus X2 W2 equals 0, right? I just expanded this to that. And then I'm just rearranging to get X2. And if I move this stuff to the other side and divide both sides by W2, I get this equation here. So this is like a direct equation for how you'd want to plot that line if this was X1 and this is X2. Is that making sense? Any questions on that? Okay. All right, so here again, minimizing RSS does not work well for linear classification. So we need a different approach. Okay, so just to review, for linear classification, we first compute the score Z, and then we threshold it if it's positive or negative to report Y hat. And the question is now, how do we design those parameters here, B and W? So what we're going to do is we're going to model the true label as a random variable that depends on Z, Z being the score here. So there's many ways to do this. The most popular version uses this probability, e to the power z over 1 plus e to the power z. So again, this is the probability that the true label is 1 given the score z. And if you plot this it looks exactly like this. This is a sigmoid curve. You can see here that this is 0, this is 1, so the probability is always somewhere between 0 and 1. And as z gets larger and positive, you get more and more confident that this label is 1. If z is 0, which we know is right on the boundary of classification, you don't know. It's with only 0.5 probability you believe y equals 1. That means with 0.5 probability you believe the alternative, y is minus 1. So this is like you have absolutely no idea between those two. But when z is less than 0, then as the magnitude gets larger and larger of that negative z, the probability that you believe y equals 1 shrinks down to 0, which means that the alternative goes up to 1. So we can also write an expression for the alternative. It's 1 minus this, which we can also write as 1 over 1 plus e to the power z. So notice that if I add these two probabilities together, they equal 1 no matter what z is. So this is something we need. For this to be a valid conditional probability mass function, we need that the sum of these two things must always equal 1, because these are the two possibilities. It's either 1 or minus 1, so no matter what z is, it has to happen with probability 1. Okay. So this is the workhorse model that people use for linear classification. Even in very sophisticated neural networks, at the very end of the day, this is the final piece of the model, is exactly this. So the larger that z is, the more likely we believe that the target is 1. And when z equals 0, it's equally likely to be 1 or minus 1. So that's the main idea. Can I answer any questions on this? So this notion of modeling labels as random is actually something that we've done before. So in regression, the model that we used to justify linear regression at the end said that the true label is, again, the same z plus some sort of error, where the error was Gaussian zero mean with some variance sigma squared. So this z here was like our, you can write it this way, x transpose, 1x transpose beta. So this notion of like a random model linking your parameters or linking z and y was something we've seen before. All we're changing is we're going from this Gaussian additive model to a different kind of randomness. All right. Any questions on what we're doing here? Okay, so this is called the logistic function, or the sigmoid. Now there's another way of writing this, which simplifies things a little bit. If you multiply top and bottom by e to the power minus z, then the top becomes 1, and the bottom becomes e to minus z plus 1. And that way, there's only one exponential. So if you're evaluating this function, computationally, exponentials take a little bit of effort to evaluate, so this one would be half the amount of work as this one. Also, for derivations, in many cases, this is simpler. Okay, no questions? Okay, don't be shy. All right, so let's try to understand a little bit about how this works. So in this case, we've been talking about the probability of y given the score z. That sort of hides maybe what we really care about, which is what's the probability of y given the feature x. So remember that in general, there's the relationship that says the score is going to be the intercept plus feature vector x times, or inner product with the weights w. If you look at the special case of a single feature, so this is for D features. Now, when D equals 1, you just get B plus X times W. So that's what we're going to study on this page, just to keep things simple. So we're going to be looking at how does this probability behave as a function first of X. So let's just make things really simple and say that the intercept term is 0. In this case, Z is just going to be X times W. And we can make some plots here. This is showing the probability as a function of X. So when you look at what happens when X is 0, you always get 0.5 probability. That happens in all these plots. So now let's see, and this is sort of that logistic sigmoid that we saw before. What happens as we, actually this is the one we saw on the previous page. That was when W is 1, in which case Z and X are the same. Now if we make W a little smaller than 1, what happens is things get sort of stretched out along the horizontal axis. On the other hand, if we make W larger than 1, the transition happens very quickly. And finally, if we change the sign of W and make it -1, then compared to this, the transition flips. Whereas X gets large, the probability gets small instead of this way. So this gives you some intuition about how that weight W affects this probability. Any questions on this? Okay. So now, of course, we were looking at B equals 0. So what happens when B is not equal to 0? The easiest way to think about that is let's first write the equation. Z is B plus WZ. Let's rewrite it a little bit as W times B over W plus X. So where is the transition now? Let me ask, is Alex Brenneman here? What about Atharva Bapat? Yeah, so what do you think? So where would this Z become 0 for which X? So based on this equation, what do I need to set X at to make Z equal 0? Okay, let me ask, is Yida Chen here? No. Let's see. What about Jake Grow?
Right here.
All right. Do you see it?
Would it just be negative B over W?
Exactly. So that means that all the intuition we have here is exactly the same, except that having X equals 0 at this point, that transition moves to minus B over W. So essentially the role of the bias just shifts this curve left or right, and the role of the weight is to make it sharper or less sharp, as well as to determine whether it goes from positive to negative or negative to positive. So those are basically how the weights and the bias work. Okay, any questions? Okay, great. So a little bit of intuition. Okay, so in order to fit the model parameters, we are going to use maximum likelihood estimation, which is something we learned about in the last unit. But as I mentioned, it's sort of the standard way by which parameters are learned in machine learning. So here we're seeing it for the second time. So at a high level, there's 2 steps to ML estimation. First, we have to define this likelihood function, which is some probability of the targets or labels given the features and the weights. And as usual here, these are our training quantities. So we always have n training samples. So this vector y is a column vector containing the labels y1 through yn. And then this matrix X has rows of x1 transpose through xn transpose. So for each data point, we have one label and one of these feature vectors. Okay, so that's the first thing, is defining a likelihood. And actually, that's what we did, right? We got our likelihood over here. This determines our likelihood function. The second thing we need to do is we need to find the b and the w that maximize that likelihood. We said often it's more tractable to minimize the negative log likelihood. And just as a quick recap of how we apply this to linear regression, we first said that the likelihood in that case was, remember this is the linear regression model here, with white noise, zero mean, variance sigma squared. In that case, the model, the probability of y given x and beta was Gaussian in the variable y, where the mean was a times beta, and the covariance matrix was sigma squared identity. So here A contains our features, but it also has a column of ones that multiplies the first element in the beta vector, the intercept term. And so if this is what we have for our likelihood, then we derived in the last unit the negative log likelihood was quadratic plus a constant term that did not contain beta. And so that means if we want to minimize this negative log likelihood over beta, we can focus on minimizing this quadratic, and that is exactly RSS. So that is why minimizing RSS is maximum likelihood for this problem, linear regression with Gaussian noise. So we're going to do exactly the same thing now for logistic regression, but what changes is we have a different model. We have that logistic model instead of this Gaussian model. Is that making sense? Any questions on ML at a high level? Okay, so we have a short derivation to do. It's not too bad. Let me lead you through it. There's something kind of tricky about this logistic regression problem in that there's no single expression for the likelihood. We really have a couple different expressions. So one of them is that the probability that the ith training label equals 1, given the features and our parameters, we said that this is this form of logistics. So we have e to the power zi over 1 plus e to the power zi. But then, for y equals minus 1, we actually had a different equation, right? So it's not like we have one common way of expressing the likelihood. So that causes us, oh, and of course, zi is going to be this. So this is the score for the ith training sample. We plug in our ith feature vector, and we apply our intercept and our weights. Okay, so the main challenge in this derivation is figuring out a way to deal with these two different mathematical forms of the likelihood. Okay, but anyway, let's get started. And what we have here is one example of these ML problems that you'll see a lot of and that often show up on exams. So let's just get started. So the very first step of our ML derivations is always to assume that the different targets in the y vector are independent of each other, conditioned on the features and the parameters. So that allows us to take this joint distribution and write it as a product of marginal or scalar distributions like this. So we go from vector y to a product of probabilities of the scalar y. And this is just the standard assumption we always employ for maximum likelihood. Is everybody with me there? Okay, So the next thing is we want to take the negative log of this. So remember, if we have a product of things, if you take the log of AB, this is equal to the log of A plus log of B. So when you have a product of n different things, you get a sum of n different logs. So that's where this product turns into a sum. Here we have the logs, here we have the minus. Okay, so now this is sort of like the tricky part is okay, this would be like the PMF. You'd be plugging in yi that is either 1 or minus 1 there. But again, we don't have a single expression. So here's a little trick that I call the switching variable. We set up this quantity yi plus 1 over 2. And remember, there's only two cases for yi. It's either 1 or minus 1. So you can see that when yi equals 1, this fraction turns into 1. But when y equals minus 1, this fraction turns into 0. So it sort of switches this term in or out of the expression depending on the value of yi. So in other words, when I put in yi equals 1, I get this. And now over here, I have 1 minus that switching variable. So if I put in yi equals minus 1, then this goes to 0. This thing turns into a 1, and I get this term. Okay, so that's the whole trick to this derivation. It allows you to go here from this sort of generic expression, the probability PMF for an arbitrary yi, 1 or minus 1, to these different expressions, the probability yi equals 1 or the probability y equals minus 1. The rest of the stuff, we'll go through it, but it's pretty straightforward algebra. But this is really the main idea on this slide. So any questions on this switching variable? Is it making sense? Yes.
Is there any difference between lowercase p for probability and uppercase PR?
Great question. So throughout my notes, I treat this probability as like the probability of some event happening. So the event happening here is when yi equals minus 1. Meanwhile, this little p is either a PMF or a PDF, depending on the context. So in this case, it's just a function where you can either plug in 1 or minus 1. So they're definitely linked, but you can see that I'm just making a distinction as to this event versus this PMF as a function of that variable. Yeah, good question. Okay, any other questions? All right, great. Okay, so let's continue. Okay, so what we have here, we have to figure this out. Natural log of this expression. So if we take the natural log of this ratio, we get natural log of the numerator minus natural log of the denominator. But natural log of the numerator is pretty easy because the log cancels the exponent and gives you zi. Natural log of the denominator is something you can't really simplify at all. Log of 1 plus e to the zi. So this is what we get for this first term here. For the next term, it's very similar. So natural log of this expression. So the numerator log of 1 is 0. And the denominator is the same as before. And now we just have to multiply some things out. So we get yi plus 1 over 2 times zi here. Get y plus 1 over 2 times this negative log, which is here. And this stuff equals 0. And finally, we have 1 times this, and minus yi plus 1 for 2 times this. And finally, you can see that a couple things cancel out. We have that this term cancels that term, which leaves us with these two terms down here. And this is about all we can do. Can't really simplify it anymore. So finally, the negative log likelihood, the thing we want to minimize, looks like this. It's a sum over our training data of this thing, which, depending on the label being 1 or minus 1, and the value of, again, the score is up here. Oh, actually, sorry. I already have it over here. So that is the form of our likelihood. Unfortunately, unlike the quadratic likelihood that we had for least squares, this is not something we can just take derivatives of and set to 0. It's not tractable that way. So in practice, we design algorithms to minimize this. And this is something we'll study in Unit 6. We will develop algorithms to minimize this negative log likelihood. But in this unit, it suffices to know that scikit-learn gives us ways of doing that, and we'll use those for the demos in the lab. Okay, but finally, this is the derivation of the thing, the loss we want to use in linear classification to optimize our parameters B and W. Okay, any questions on the derivation? Okay, so let's see how well this works. So we'll come back to our asymmetric data set from before. This is the one that broke least squares. This is least squares on the top. Remember how this line is skewed to the right, and so when this is the score Z, and so when you threshold the score Z to get y hat, your y hats don't even match the training data. So now, once we plot the same score, but for the coefficients B and W from logistic regression, minimizing the ones that minimize this expression, we actually get this line. This is our score Z. It's still linear as before, because that's what we always have for linear regression. So Z, oh yeah. So this is still linear. This. And then we threshold it. So whenever this line is positive, that's anywhere from this to the right, we set y hat. This is y hat in green. We set y hat to 1, and whenever z is less than 0, which is x to the left of here, we set y hat to 0. And so here we're perfectly matching our training data. The decision threshold is basically transitioning exactly halfway our points. Even though there's this one out here, it is not distracting the criterion. And we're plotting one more thing here, which is the probabilistic model. This is the probability that yi equals 1. And you can see that when we're right on the boundary here, when z equals 0, it's exactly 0.5, like we expect. And as our feature goes to the right, we're more and more confident about how to classify that feature. And so when we're out here, we're extremely confident that this deserves the label y equals 1. Over here, for this feature, you can see we're not that confident. It's like maybe like 75% confident that this corresponds to 1, but there's a chance that because our model has uncertainty, there's actually a chance that we could have had a -1 there, according to this model. Okay, so that is that's the method, and this is just a summary because it's an important equation. Here I've put it in a box, and this is exactly what we derived a couple pages ago. This is when yi is -1 and 1. You can also, in many sources, you'll see a similar derivation or results when the labels are 0 and 1, and you have a slightly different expression. The thing that changes is the switching variable. So this was the switching variable we needed over here when y is plus or -1. And if we would have redone the derivation for this, the switching variable would have just been yi. And you can see it's very similar. It's just that it changes here and here. Yeah. So depending on how your labels are set up, you need to use the right one of these expressions. And finally, this is often known as binary cross entropy loss. There's a sort of reason behind this terminology that I won't get into at the moment, but this is the most common term for this loss, the thing that you minimize to do logistic regression. All right. I think that's enough for today. See you guys on Wednesday. If you have any questions, come up and ask.